25. Continental Europe. The first railway service outside the United Kingdom and North America was opened in 1829 in France between Saint-Étienne and Lyon. It was initially limited tonal traction. The first steam locomotive in service in Europe was named the Elephant, which on the 5th of May, 1835 hauled a train on the first line in Belgium, linking Mechelen and Brussels. Photo of the Adler made in the early 1850s in Germany. The first working steam locomotive was a rack and pinion engine similar to the Salamanca, designed by the British locomotive pioneer John Blenkinsop. Built in June 1816 by Johann Friedrich Krieger in the Royal Berlin Iron Foundry, Königlich-Eisengesserie zu Berlin, the locomotive ran on a circular track in the factory yard. It was the first locomotive to be built on the European mainland and the first steam-powered passenger service. Curious onlookers could ride in theatric coaches for a fee. It is portrayed on a New Year's badge for the Royal Foundry dated 1816. Another locomotive was built using the same system in 1817. They were to be used on pit railways in Königsut and in Louisenthal on the Saar, today part of Völklingen, but neither could be returned to working order after being dismantled, moved and reassembled. On the 7th of December, 1835, the Adler ran for the first time between Nuremberg and Fürth on the Bavarian Ludwig Railway. It was the 118th engine from the locomotive works of Robert Stephenson and stood under patent protection. First locomotive in Russia. 1834 in Russia, the first steam locomotive was built in 1834 by Cherpanovs. The first Russian Tsarskoye Selo steam railway started in 1837. In 1837, the first steam railway started in Austria on the Emperor Ferdinand Northern Railway between Vienna Floridsdorf and Deutsch-Wagram. The oldest continually working steam engine in the world also runs in Austria. The GKB 671 built in 1860 has never been taken out of service, and is still used for special excursions. In 1838, the third steam locomotive to be built in Germany, the Saxonia, was manufactured by the Maschinenbau firma Ubigor near Dresden, built by Professor Johann Andreas Schubert. The first independently designed locomotive in Germany was the Buth, built by August Fortzieg in 1841. The first locomotive produced by Henschel Werk in Kassel, the Drach, was delivered in 1848. The first steam locomotives operating in Italy were the Bayard and the Vesuvio, running on the Napoli-Portici line, in the Kingdom of the Two Sicilies. The first railway line over Swiss territory was the Strasbourg-Basel line, opened in 1844. 3 years later, in 1847, the first fully Swiss railway line, the Spanish Sprochlebahn, from Zurich to Baden was opened. Components. The main components of a steam locomotive. Click to enlarge. Key to numbered components. No.item. 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 No.item 1 tender 13 smoke box door 25 valve 37 coal bunker 2 cab 14 trailing truck / rear bogie 26 valve chest / steam chest 38 grate / fire grate 3 safety valves 15 running board / footboard 27 firebox 39 ash pan hopper 4 reach rod 16 frame 28 boiler tubes 40 journal box 5 whistle 17 brake shoe 29 boiler 41 equalizing beams / equalizing levers / equalizing bars 6 generator / turbo generator 18 sand pipe 30 superheater tubes 42 leaf springs 7 sand dome 19 side rods / coupling rods 31 regulator valve / throttle Valve 43 driving wheel / driver 8 throttle lever / regulator lever 20 valve gear / motion 32 superheater 44 pedestal / saddle 9 steam dome 21 connecting rod / main rod 33 smokestack / chimney 45 blast pipe 10 air pump / compressor 22 piston rod 34 headlight 46 pilot truck pony truck if single axle, / leading bogie 1 smoke box 2 3 piston 3 5 brake hose 47 pilot / cow catcher 12 steam pipe 24 cylinder 36 water compartment 48 coupler / coupling. Descriptions of these components are here. Boiler. The fire tube boiler was standard practice for steam locomotive. Although other types of boiler were evaluated, they were not widely used, except for some 1,000 locomotives in Hungary which used the water tube Britain boiler. A steam locomotive with the boiler and firebox exposed, firebox on lift. A boiler consists of a firebox where the fuel is burned, a barrel where water is turned into steam, and a smoke box which is kept at a slightly lower pressure than outside firebox. Solid fuel, such as wood, coal or coke, is thrown into the firebox through a door by a fireman, onto a set of grates which hold the fuel in a bed as it burns. Ash falls through a grate into an ashpan. If oil is used as the fuel, a door is needed for adjusting the airflow, maintaining the firebox, and cleaning the oil jets. The fire tube boiler has internal tubes connecting the firebox to the smoke box through which the combustion gases flow, transferring heat to the water. All the tubes together provide a large contact area, called the tube heating surface, between the gas and water in the boiler. Boiler water surrounds the firebox to stop the metal from coming too hot. This is another area where the gas transfers heat to the water and is out the firebox heating surface. Ash and char collect in the smoke box as the gas gets drawn up the chimney, stack or smokestack in the US, by the exhaust steam from the cylinders. The pressure in the boiler has to be monitored using a gauge mounted in the cab. Steam pressure can be released manually by the driver or fireman. If the pressure reaches the boiler's design working limit, a safety valve opens automatically to reduce pressure, 26, and avoid a catastrophic accident. The exhaust steam from the engine cylinders shoots out of a nozzle pointing up the chimney in the smoke box. The steam entrains or drags the smoke box gases with it, which maintains a lower pressure in the smoke box than that under the firebox grate. This pressure difference causes air to flow up through the coal bed and keeps the fire burning. Aftermath of a boiler explosion on a railway locomotive. C. 1850. The search for thermal efficiency greater than that of a typical fire tube boiler led engineers, such as Nigel Gresley, to consider the water tube boiler. Although he tested the concept on the owner class W1, the difficulties during development exceeded the will to increase efficiency by that route. The steam generated in the boiler not only moves the locomotive, but is also used to operate other devices such as the whistle, the air compressor for the brakes, the pump for replenishing the water in the boiler, and the passenger car heating system. The constant demand for steam requires a periodic replacement of water in the boiler. Water is kept in a tank in the locomotive tender or wrapped around the boiler in the case of a tank locomotive. Periodic stops are required to refill the tanks. An alternative was a scoop installed under the tender that collected water as the train passed over a track pan located between the rails. While the locomotive is producing steam, the amount of water in the boiler is constantly monitored by looking at the water level in a transparent tube, or sight glass. Efficient and safe operation of the boiler requires keeping the level in between lines marked on the sight glass. If the water level is too high, steam production falls, efficiency is lost, and water is carried out with steam into the cylinders, possibly causing mechanical damage. More seriously, if the water level gets too low, the crown, top, sheet of the firebox becomes exposed. Without water on top of the sheet to transfer away the heat of combustion, it softens and fails, letting high-pressure steam into the firebox and the cab. The development of the fusible plug, a temperature-sensitive device, ensured a controlled venting of steam into the firebox to warn the fireman to add water. Scale builds up in the boiler and prevents adequate heat transfer, and corrosion eventually degrades the boiler materials to the point where it needs to be rebuilt or replaced. Startup on a large engine may take hours of preliminary heating of the boiler water before sufficient steam is available. Although the boiler is typically placed horizontally, for locomotives designed to work in locations with steep slopes, it may be more appropriate to consider a vertical boiler or one mounted such that the boiler remains horizontal but the wheels are inclined to suit the slope of the rails. Steam circuit. Thermal image of an operating steam locomotive. The steam generated in the boiler fills the space above the water in the partially filled boiler. Its maximum working pressure is limited by spring-loaded safety valves. It is collected either in a perforated tube fitted above the water level or by a dome that often houses the regulator valve, or throttle, the purpose of which is to control the amount of steam leaving the boiler. The steam then either travels directly along and down a steam pipe to the engine unit or may first pass into the wet header of a superheater, the role of the latter being to improve thermal efficiency and eliminate water droplets suspended in the saturated steam, the state in which it leaves the boiler. On leaving the superheater, the steam exits the dry header of the superheater and passes down a steam pipe, entering the steam chests adjacent to the cylinders of a reciprocating engine. Inside each steam chest is a sliding valve that distributes the steam via ports that connect the steam chest to the ends of the cylinder space. The role of the valves is twofold: admission of each fresh dose of steam, and exhaust of the used steam once it has done its work. The cylinders are double acting, with steam admitted to each side of the piston in turn. In a two-cylinder locomotive, one cylinder is located on each side of the vehicle. The cranks are set 90 degrees out of phase. During a full rotation of the driving wheel, steam provides 4 power strokes. Each cylinder receives 2 injections of steam per revolution. The first stroke is to the front of the piston and the second stroke to the rear of the piston, hence 2 working strokes. Consequently, 2 deliveries of steam onto each piston face in the 2 cylinders generates a full revolution of the driving wheel. Each piston is attached to the driving axle on each side by a connecting rod, and the driving wheels are connected together by coupling rods to transmit power from the main driver to the other wheels. Note that at the 2 dead centers, when the connecting rod is on the same axis as the crank pin on the driving wheel, the connecting rod applies no torque to the wheel. Therefore, if both cranksets can't be at dead center at the same time, and the wheels should happen to stop in this position, the locomotive could not start moving. Therefore, the crank pins are attached to the wheels at a 90 degrees angle to each other, so only one side can be at dead center at a time. Each piston transmits power through a crosshead, connecting rod, main rod in the US, and a crank pin on the driving wheel, main driver in the US, or to a crank on a driving axle. The movement of the valves in the steam chest is controlled through a set of rods and linkages called the valve gear, actuated from the driving axle or from the crank pin. The valve gear includes devices that allow reversing the engine, adjusting valve travel and the timing of the admission and exhaust events. The cutoff point determines the moment when the valve blocks a steam port, cutting off admission steam and thus determining the proportion of the stroke during which steam is admitted into the cylinder. For example, a 50% cutoff admits steam for half the stroke of the piston. The remainder of the stroke is driven by the expansive force of the steam. Careful use of cutoff provides economical use of steam and in turn, reduces fuel and water consumption. The reversing lever, Johnson bar in the US, or screw reverser, if so equipped, that controls the cutoff, therefore, performs a similar function to a gearshift in an automobile maximum cutoff, providing maximum tractive effort at the expense of efficiency, is used to pull away from a standing start whilst a cutoff as low as 10% is used when cruising, providing reduced tractive effort, and therefore lower fuel /water consumption. 27. Exhaust steam is directed upwards out of the locomotive through the chimney, by way of a nozzle called a blast pipe, creating the familiar chuffing sound of the steam locomotive. The blast pipe is placed at a strategic point inside the smoke box that is at the same time traversed by the combustion gases drawn through the boiler and grate by the action of the steam blast. The combining of the two streams, steam and exhaust gases, is crucial to the efficiency of any steam locomotive, and the internal profiles of the chimney, or, strictly speaking, the ejector, require careful design and adjustment. This has been the object of intensive studies by a number of engineers, and often ignored by others, sometimes with catastrophic consequences. The fact that the draft depends on the exhaust pressure means that power delivery and power generation are automatically self-adjusting. Among other things, a balance has to be struck between obtaining sufficient draft for combustion whilst giving the exhaust gases and particles sufficient time to be consumed. In the past, a strong draft could lift the fire off the grate, or cause the ejection of unburned particles of fuel, dirt and pollution for which steam locomotives had an unenviable reputation. Moreover, the pumping action of the exhaust has the counter effect of exerting back pressure on the side of the piston receiving steam, thus slightly reducing cylinder power. Designing the exhaust ejector became a specific science, with engineers such as Chapelon, Gieser and Porter making large improvements in thermal efficiency and a significant reduction in maintenance time. 28, and pollution. 29. A similar system was used by some early gasoline/kerosene tractor manufacturers. Advance only /hard par. The exhaust gas volume was vented through a cooling tower, allowing the steam exhaust to draw more air past the radiator. Running gear. Running gear animation steam locomotive 2-8-2 at train station steam cleaning the running gear of an H-class locomotive, Chicago and Northwestern Railway, 1943. Running gear includes the brake gear, wheel sets, axle boxes, springing and the motion that includes connecting rods and valve gear. The transmission of the power from the pistons to the rails and the behavior of the locomotive as a vehicle, being able to negotiate curves, points and irregularities in the track, is of paramount importance. Because reciprocating power has to be directly applied to the rail from 0 RPM upwards, this creates the problem of adhesion of the driving wheels to the smooth rail surface. Adhesive weight is the portion of the locomotive's weight bearing on the driving wheels. This is made more effective if a pair of driving wheels is able to make the most of its axle load, i.e. its individual share of the adhesive weight. Equalizing beams connecting the ends of left springs have often been deemed a complication in Britain. However, locomotives fitted with the beams have usually been less prone to loss of traction due to wheel slip. Suspension using equalizing levers between driving axles, and between driving axles and trucks, was standard practice on North American locomotives to maintain even wheel loads when operating on uneven track. Locomotives with total adhesion, where all of the wheels are coupled together, generally lack stability at speed. To counter this, locomotives often fit unpowered carrying wheels mounted on two-wheeled trucks or four-wheeled bogies centered by springs /inverted rockers /geared rollers that help to guide the locomotive through curves. These usually take on weight off cylinders at the front or the firebox at the rear when the width exceeds that of the main frames. Locomotives with multiple coupled wheels on a rigid chassis would have unacceptable flange forces on tight curves, giving excessive flange and Running gear of steam locomotive rail wear, track spreading and wheel climb derailments. One solution was to remove or thin the flanges on an axle. More common was to give axles end play and use lateral motion control with spring or inclined plane gravity devices. Railroads generally preferred locomotives with fewer axles, to reduce maintenance costs. The number of axles required was dictated by the maximum axle loading of the railroad in question. A build